I will be solving problem 1, the McCabe-Thiele problem of take-home exam 3. In our problem statement, we are given feed rate in, mole percent of ethyl alcohol in the feed, mole percent of ethyl alcohol in the distillate, and the fact that 90% recovery of alcohol from the feed occurs in the distillate. We are also given that feed is a saturated liquid, pressure is 1 atm, and L/D equals 3. We want to find steam requirement, number of theoretical stages, optimal feed stage, and minimum reflux ratio. I left equilibrium data out of this frame for sizing purposes and so that it could be used elsewhere for graphing. This is a diagram of the distillation column in the problem statement. Here we can see that feed in occurs at the bottom plate. The feed rate in is 100 kmoles per hour. The feed contains 12 mole percent ethyl alcohol and therefore 88 mole percent water. We need to solve a couple material balances to determine values in order to solve the given problems. We know that feed in is equal to distillate out and bottoms out. Our initial conditions give that there is 90% recovery of alcohol in the distillate. Multiplying 0.9 by mole percent of alcohol in the feed and total values for feed give us the molar flow rate of alcohol in the distillate, which is 10.8 kmoles per hour. We solve alcohol in the bottoms by subtracting initial amount of alcohol in the feed by the amount of alcohol in the distillate, giving us 1.2 kmoles per hour. The distillate total molar flow rate is found by using a ratio of the amount of alcohol in the distillate over the mole fraction of alcohol in that flow. This is found to be 12.706 kmoles per hour. Total bottoms molar flow rate is found by subtracting distillate flow rate from feed flow rate, giving 87.294 kmoles per hour in the bottoms. To solve for the mole percent of alcohol in the bottoms, we just use the flow rate of alcohol over the total flow rate in the bottoms, giving us XB equal to 0.01375. Part A of the problem wants us to solve for the steam requirement in kilomoles per hour. We can see that vapor is equal to liquid plus distillate flows, which are highlighted in the diagram shown. We are also given that L/D is 3, so we multiply D, which is 12.706 by 3, and get that liquid flow rate from the reflux back into the column. To solve for vapor, we add L plus D and get that B is equal to 50.824 kilomoles per hour. Part B of the problem wants us to find the number of theoretical stages. In order to do this, we must plot 5 lines: the equilibrium curve, 45-degree line, Q line, rectifying section operating line, and the stripping section operating line. We are given the equilibrium data and can enter all of this into Excel to generate a curve like the one seen in the graph below. The X values refer to liquid mole fraction and Y refers to vapor mole fraction. The second line we must plot is the 45-degree line, which is just Y equals X from 0 to 1, and the third line we must plot is the Q line. The Q line refers to the feed operating line, and Q refers to the quality of the feed. The problem statement states that the inlet stream is a saturated liquid, and therefore the slope of Q is 1. Given data also includes that mole percent of alcohol in is 12, or XF is equal to 0.12. We can see the Q line on the same graph. The fourth line we must graph is the rectifying section operating line. We know that Y is equal to the first equation shown. However, we also know that R divided by R plus 1 is equal to L divided by V, and 1 divided by R plus 1 is equal to L/D. We know that L/D is 3, and the mole fraction of alcohol in the distillate is 0.85 from the problem statement. And so we plug in the R value and XD to the second equation and get that Y is equal to 0.75 times X plus 0.2125. This equation is plotted on the graph from the Q line at 0.12, 0.3025 to the point on the 45-degree line that mole fraction of alcohol in distillate occurs, or at the point 0.85, 0.85. The final line that must be graphed is the stripping section operating line. This line begins at the point on the 45-degree line that mole fraction of alcohol in the bottoms occurs, 0.01375, 0.01375, and ends at the point on the Q line that the rectifying section ended, or 0.12.3025. This line is plotted on the graph below. Now that we have all of our lines graphed, we can draw our step-off stage lines to determine number of theoretical equilibrium stages. The very top of the diagram is extremely small and difficult to draw our lines on, so I zoomed in on the graph and drew the lines separately, as shown on the bottom picture. I found that the top of the rectifying line to the second highest equilibrium point graphed had about 10 stages. I noted that in the brackets on the uppermost diagram and continued the step-off lines from there. In the end, I found the number of theoretical stages to be just above 21, because the number of times the step-off line touched the equilibrium curve was about 21. Part C of the problem asks us to determine the optimal feed stage. This occurs at the point on the diagram that crosses the Q line, or where the rectifying section of the graph changes to the stripping section. The arrow on the graph shows that this occurs at stage 19. Finally, Part D of the problem wants us to determine L over D min. This can be found by drawing a tangent line of the equilibrium curve that passes through the initial point in the rectifying line at 0.85, and equilibrium point at 0.7472, 0.7815. The slope between these 2 points is determined to be 0.6663, which is also equal to L over V min. The equation for L over D min is found to equal 1 over the inverse of L over V min minus 1, so we plug in 0.6663 to this equation and get that L over D min is about 1.997. That is how you find the steam requirement, number of theoretical stages, optimal feed stage, and minimum ratio of liquid over distillate. Thank you for your time.